Hello everyone. Today we are going to look at the first part of chapter 22, which is on electric current. So our learning targets today are to define electric current, examine the characteristics of an electric circuit. And the questions that we are hoping to answer today: what is electric current? Why does electric current flow? And what are the necessary components of an electric circuit? So let's go ahead and jump right in. And you know that I always like to start with the review stuff so it's in your head. So the law of conservation of energy. So remember that electricity is another type of energy, and so we need to think about all the things we already know about energy. So the law of conservation of energy tells us that energy cannot be created or destroyed, but it can change forms or be transferred. And what we're going to look at today is this idea of changing forms. Okay? So another review question for you. Of the three subatomic particles we are working with, so those would be protons, neutrons, and electrons, which is the easiest to move and why? Have you got an idea? Good. So electrons are the easiest to move. Why? Well, for a couple of reasons. One, they're the smallest. They're also the lightest. L-I-G-H-T-E-S-T, sorry. And they're on the outside of the atom. So remember, our atom looks like this, with protons and neutrons in the middle and electrons on the outside. So they're the smallest, the lightest, and they're already on the edge of the atom. Okay? Now, do you remember why electrons would leave an atom? Why would those electrons jump off? Yep, good for you. They absorb energy. So think about the Van de Graaff, right? There's some friction underneath the top of that Van de Graaff. It gets the electrons all excited from all that extra energy from the friction, and they just jump right off that atom. So that's why electrons are the ones that leave. They absorb that energy. All right, so let's move on to the new stuff here. So we'll look at questions 1 and 2. What is electric current, and why does electric current flow? So, what is electric current? This is just, kind of a basic definition, and then we'll talk a little bit more specifically. So, electric current is the movement of charge. And we are specifically talking about electrons again. So we're specifically talking about negative charges moving around, and that's an electric current, okay? And electric currents move because of an imbalance of energy, not in energy, my bad, of energy. Okay, so let's look at how that happens. So here we have a really simple diagram. We've got our battery here, right? And there's a chemical reaction that happens inside the battery. So there's a chemical thing going on with some battery acid and some copper and some zinc, okay? But what happens is that all the negatives accumulate on one end of this battery, leaving all the positives on the other end of the battery, okay? And you know what happens when you have a positive and a negative, right? They're attracted to each other. So then negatives can't move this way because of the chemical reaction happening. So that's not a possibility. So if I give those electrons somewhere to go, I attach a wire here, for example. Those electrons are going to travel toward the protons, right? They're going to be attracted. And so as the electrons are traveling around, they are an electric current, and that they just keep going and going and going and going. The chemical reaction here keeps on producing negatives on one side and positives on the other side. And so until that chemical reaction is all used up, this battery is going to produce negatives, right, electrons down here on this end. And if we give them somewhere to go, they're going to go, right, because they're all pushing away from each other, they're all repelling each other, and they're going to have this path to travel on. Okay, so that is how a battery specifically works. Current in your wall works a little bit differently, but it's the same idea. There's a path for those electrons to travel on. Okay, so what does a battery do? A battery creates what's called an electrical potential difference, which is the same way of saying a potential energy, right? So we know that there's gravitational potential energy when you lift something up off the ground. Well, there's also electrical potential energy that happens when you separate the electrons and the protons. Okay? So when we make that electrical potential energy do work for us, then we have created an electric circuit. All right, so let's see how that works. So here we have the same diagram, except this time there's a light bulb in this diagram. So I still have an accumulation of negative charges here, which leaves me a lot of positive charges on this end. All right, I'm still going to hook up a wire so those electrons have somewhere to go. They're still going to be attracted to the positive end, so they're still going to travel like this. But because I put the light bulb in there, they can't go straight through. And so what's going to happen is they're going to go up here into the light bulb, through this little wire here, down and out of the light bulb, and continue on their way. So here I have electrical energy, but here I have light energy. And then as it comes back into the wire, it changes back to electrical energy. Okay, does that make sense? So that's our law of conservation of energy, right? It's electrical energy until it's light energy, and there's also a little bit of heat there, right, if you've ever touched a light bulb. And then it goes back to electrical energy, and then it comes back into the battery. And this is an example of electrical energy doing work for us, right? The work is that the light bulb lights up, and so that is a circuit. All right, so let's summarize. Here's our example. And so what are we going to say? We are going to say that the electrons move from the battery as electric energy through the wire, still as electric energy, into the light bulb, and in the light bulb they change to light energy, and then after they go through the light bulb, they go back to the wire, and then to the positive end of the battery. Okay, think that over for just a minute. Does that make sense to you? All right, so what we would say is that the electric current, right, the electric current, that's the movement of electrons. That's electrical energy. The circuit, let me change colors. The circuit is the whole thing, right? The whole thing, the electrons moving through the wire, making light in the light bulb, going back into the wire, back to the battery. That's the circuit. The current, the electric current, is this electrical energy moving through the wires. All right, does that difference make sense in your head? Okay. So here's the your turn question. What is the difference between an electric current and an electric circuit? So pause the video, answer the question, turn it back on when you're ready. All right. So let's take a look at this second or third question here, I guess. What are the necessary components of an electric circuit? So an electric circuit has 3 necessary components. So let's talk about those. It has to have a source of electrons. All the things that we build in class are going to use a battery as their source of electrons, but you could plug something into a wall, or you could hook it up to a solar panel. You know, that would be a source of electrons as well. All electric circuits have to have a path. We're usually going to use wire. That's pretty common. We have to have a path for the electrons to travel on. And then finally you have to have a device, right? That electricity has to do something for you. So a device to use the energy. It could be a light bulb. That's often what we're going to do, but it could also be like a motor or a fan. It could be a doorbell. It could be a radio. It could be a phone, right? So there's something that's going to use that energy. All right. So if we take a look at our simple circuit here, we can see we've got a battery. That's our source. We've got a light bulb here. That's our device. And then we have a path for the electrons to travel on, and that's the wire. This particular wire has a switch in it, and as long as that switch is closed, then the electrons can go through, and it is a complete circuit, right, because the path goes all the way around. If we were to open up that switch, then the electrons would get stuck up here, and the light bulb would go off, and that would be an incomplete circuit because the electrons can't get all the way around. But like I said, as long as this switch is closed, then we have a complete circuit. All right, so 3 of the characteristics of a circuit that we can measure. You didn't think you were going to get through this whole unit without any math, did you? So what we can measure the current. That's how many electrons are flowing in the circuit. We can measure the voltage. The voltage is how much potential energy is in the battery. And we can measure the power, or the rate at which work is done. Okay? So current is the amount of electrons. You know what? I should give myself a box, shouldn't I? Let's try that again. Amount of electrons in the circuit. We abbreviate that with an I, a capital I for current. I know that doesn't make any sense, but that's the way it goes. I'm not in control of that. And I apologize if that's going to be difficult for you to remember, but it's an I for current. Okay? We measure current in something called amperes, which is a capital A. Okay? Voltage is the potential energy, or the potential difference in the source. And we use a capital V for voltage. Now remember, a lowercase v is velocity, so it's really important that you use a capital V, right? And then we also measure this in volts, which is a capital V. So a capital V is both for voltage and volts. That's not too hard to remember. Okay, and then we already know that power is the rate at which work is done. We're going to use a capital P for power. Remember that that is not momentum anymore, right? This is power. And you already know that we're going to measure this in units called watts, which is a capital W. Okay? Now, as you might guess, those things are all related to each other, and so the formula that uses all of those concepts, P equals I times V. So power is current times voltage. Or you could solve for I, and you get I equals P over V. That's P. Or you could solve for V, in which case you'd get voltage is equal to power over current. Okay, so any of those, they're all really the same formula. Let me clean this up just a little bit. They're all really the same formula. It just depends on how you want to write it. Okay, so let's look at example problem number 1. A 75-watt electric light bulb is connected to a 125-volt outlet. Calculate the current moving through the circuit. So what do I know? I know that the power is 75 watts. That's not a negative sign there. It's just a dash. You'll often see that. I really don't know why. The voltage is 125 volts. And the current is what we're looking for. Okay? So here's my formula. P equals I times V. But I am going to use this version of it where I have I already by itself. So I'm going to use I equals P over V. I'm going to plug in my 75, my 125. So I've got 75 watts divided by 125 volts. And that gives me 0.625 or 0.63. And because this is current that I'm finding, I'm going to label it A for amperes. Okay? So, for your turn, there are 2 questions here. Does the picture show a complete circuit that would work? Please explain your answer. And then there is a problem for you to calculate. As always, please write down any questions that you have about the notes, and we will talk about them in class next time. So, thank you very much, and I will see you soon.